Hello everyone, I'm Mike DiVerde and I'm an aerospace engineer. Today I'm wearing my 777X shirt. I'm a design engineer at Boeing and I worked on the antenna installations for the 777X. In today's episode of Robots in Space, we will discuss the Juno spacecraft and its flyby of Io, along with some recent research on volcanism on that moon of Jupiter. A side note, I've always thought it was pronounced Io. I'm seeing the preferred is Io. Apparently they're interchangeable, but if I switch back and forth, you'll know why. Juno uses a spinning solar-powered spacecraft in a highly elliptical polar orbit that avoids most of Jupiter's high-end radiation regions. Although the main spacecraft was built by Lockheed Martin, Juno's instruments and components came from all over the world. Juno shipped in pieces to the Kennedy Space Center in Florida, where it was assembled and put on top of the Atlas V 551 rocket that blasted it off into space. While building the spacecraft, engineers took extreme care to keep it clean. They worked in a clean room and wore special suits that prevent dirt, dust, and hair from contaminating the craft. Engineers tested every part of the spacecraft to ensure that it survives the harsh environment of outer space. They simulated the conditions that Juno may encounter in test chambers. For example, they tested how well components can withstand heat and vibration, a test often called shake and bake. The Jovian Infrared Auroral Mapper, JIRAM, studies Jupiter's atmosphere in and around the auroras, learning more about the interactions between the auroras, the magnetic field, and the magnetosphere. JIRAM will be able to probe the atmosphere down to 30 to 45 miles below the Jovian cloud tops, where the pressure is 5 to 7 times greater than at Earth's sea level. JIRAM consists of a camera and a spectrometer, which splits light into its component wavelengths like a prism. The camera will take pictures in infrared light, which is heat radiation, with wavelengths of 2 to 5 microns. In particular, the instrument will snap photos of auroras at a wavelength of 3.4 microns, the wavelength of light emitted by excited hydrogen ions in the polar regions. Methane in the atmosphere absorbs light at the same wavelength, darkening the atmosphere behind the auroras. In front of a darkened background, the auroras stand out even more brightly. The instrument will also try to learn about the structure and origin of voids in Jupiter's atmosphere called hotspots. By measuring the heat radiating from Jupiter's atmosphere, JIRAM can determine how water-containing clouds circulate under the surface. It turns out that this sort of motion, called convection, in which hot gas rises and cool gas sinks, reveals the amount of water in these clouds. Certain gases in the atmosphere, methane, water, ammonia, and phosphine in particular, absorb certain wavelengths of infrared light. When the spectrometer measures the infrared rainbow emitted by Jupiter, the wavelengths of light absorbed by those gases would be missing. The missing wavelengths indicate the chemical composition of the atmosphere. JIRAM was developed by the Italian National Institute for Astrophysics and funded by the Italian Space Agency. Designed to capture remarkable pictures of Jupiter's cloud tops, Juno's color visible light camera, called JunoCam, will see what you would see if you were an astronaut orbiting Jupiter. As Juno's eyes, it will provide a wide view, helping to provide context for the spacecraft's other instruments. Because Juno rotates a couple of times per minute, its images would smear if it were to try to take a complete picture at once. Instead, it is a push broom imager, taking thin strips of an image at the same rate that the spacecraft spins. JunoCam then stitches the strips together to form the full picture. JunoCam takes images only during closest approach, about 3,100 miles above the cloud tops, when it gets the best vantage point possible. Taking pictures with a resolution of up to 16 miles per pixel, the wide-angle camera will provide incredible new views of Jupiter's atmosphere. JunoCam is provided by Malin Space Science Systems. The north polar region of Jupiter's volcanic moon Io was captured by NASA's Juno during the spacecraft's 57th close pass of the gas giant on December 30th, 2023. The region was imaged at a scale of 1.1 miles per pixel. The low illumination angle along the terminator shows several previously unrecognized mountain blocks rising abruptly above the surrounding plains. These are each characterized by a central sharp peak and adjacent flanks that appear to be collapsing towards plains. The highest of these peaks range is 6.1 miles tall. The shadows indicate that some of the mountain flanks grade into plateaus under 0.6 miles tall. While mountains here are partly or completely covered by bright white diffuse deposits, which may be sulfur dioxide frosts derived from gases escaping the interior and transported up. Extremely large flow fields are evident here. The most active flow regions in Lake Fluctus are evidenced by their darker color and surrounded by white deposits, perhaps liberated from the surface by thermal action. Now we will watch a video on Io while listening to Spectral Valkyrie sing the song entitled Leviathan. Enjoy.
Slouching beast can't stay afloat. Her top is too heavy, too weak to flatten all her scales in this liquidity. She hid within attention, ate her tail to stay alive. And all those men who prayed to play were swallowed in her hide. Leviathan, she doesn't care for blood or refugees. She only wants to carry on like
These composite views depicting volcanic activity on Io were generated using both visible light and infrared light collected by NASA's Juno spacecraft during flybys of the Jovian moon on December 14th, 2022 on the left, and March 1st, 2023. In both views, the view of the moon in mottled grays and browns is provided by the JunoCam imager. The overlays of reds, yellows, and bright whites is data from spacecraft's JIRAM. That's the Jovian Infrared Auroral Mapper instrument. The JIRAM data on the left was collected from an altitude of about 50,000 miles with a spatial resolution of around 12 miles per pixel. The JIRAM data annotated into the right JunoCam image was acquired at an altitude of about 36,000 miles and has a spatial resolution of 9 miles per pixel. JIRAM sees infrared light not visible to the human eye. It measures heat radiated from the planet at an infrared wavelength of around 5 microns. Quoting from a research paper entitled JIRAM Observations of Volcanic Flux on Io, Distribution and Comparison to Tidal Heat Flow Models. Our study uses data from an infrared camera on Juno called the Jovian Infrared Auroral Mapper, JIRAM, to image Io, the innermost Galilean moon of Jupiter. Io is the most volcanically active body in the solar system. Io's volcanoes are powered by both the extreme tides from Jupiter and the gravitational interactions between it and Jupiter's other moons. These tides generate friction inside Io. Simulations of Io's interior suggest that, depending on how deep that friction is being generated, the surface heat flow will be higher in certain areas. Using JIRAM, we have mapped where volcanoes are producing the most power and compared that to where we expect higher heat flow from the interior models. Our map doesn't agree with any of these models very well. JIRAM observed more volcanic activity at the poles than we expected to see based on previous observations. However, since the South Pole was only observed twice, it's possible that these observations don't represent the average volcanic activity of the South Pole. Very bright volcanoes that may have been continuously active for decades were also imaged during these Juno flybys, some of which are nearer the poles than the equator. Our study produced a globally complete map of the flux produced by volcanic hotspots. Viewing this flux on both a linear and a logarithmic scale better illustrates individual volcanic behavior and global heat flow variations, particularly the lowest flux regions. This map includes several interesting bright volcanic features. While we do not attempt to identify all the volcanoes we measure, we are able to determine identities for these particularly bright features. The bright circle centered near 300 west, 20 north is Loki, the brightest and largest persistent volcano on Io. Quoting from the research paper entitled Using Io's Sulfur Isotope Cycle to Understand the History of Tidal Heating. Io is a moon of Jupiter. It is the most volcanically active body in our solar system. Io is in an orbital resonance with two other large moons of Jupiter, Europa and Ganymede. Every time Ganymede orbits Jupiter once, Europa orbits twice, and Io orbits 4 times. This situation causes tidal heating in Io, like how the moon causes ocean tides on Earth, which causes the volcanism. We don't know how long this resonance has been occurring and whether what we observe today is normal. This is because the volcanism renews Io's surface all the time, leaving little trace of the past. We use the isotopes of sulfur as a tracer of tidal heating on Io because sulfur is released through volcanism, processed in the atmosphere, and recycled into the mantle. We build a numerical model to simulate the sulfur isotope cycle on Io. Recent measurements of the sulfur isotopic composition of Io's atmosphere allows us to constrain a likely evolution for Io over time. We find that tidal heating on Io has occurred for billions of years, and that the variability of the sulfur isotopic composition of the atmosphere may indicate the average tidal heating rate on Io. On Io, sulfur, mostly as sulfur dioxide, is the dominant volatile species. It covers the surface as frost, forms the main constituent of the atmosphere, is emitted from the many volcanoes, and escapes from the atmosphere to populate Io's orbit as plasma. Additionally, the natural isotopic abundances of the two most common stable isotopes of sulfur are sufficiently abundant. 32 sulfur is about 95%, and 34 sulfur is about 5%. That millimeter and/or spacecraft observations and sampling can detect and measure the isotopologues of sulfur-bearing species. Hence, measurements of sulfur isotopes in the frost, atmosphere, and/or volcanic plumes of Io could be used to further our understanding of the geological history of Io. So here is my summary. Some of Jupiter's moons are in orbital resonance, and gravity from Jupiter on one side and the moons on the other side causes Io to get squeezed like an accordion. This tidal gravitational force heats up Io's interiors through friction, and the heat builds up until gases burst through a vent in the crust. Io's atmosphere cycles its temperature around the freeze sublimation point of sulfur compounds, which leads to enrichment of some isotopes of sulfur over eons. Researchers use the data collected by Juno to estimate that this process has been going on for over 1.5 billion years. Omni, futurists,